All right, rather than finding non-constant control limits for the CUSUM, it is easier to transform the CUSUM to a different score for which the control limit is constant. And this new score is called the mean adjusted CUSUM. We actually need two of them because we need to test for an increase and for a possible decrease, right? Since we're subtracting something each time, we need to either subtract or add something, or subtract something from the negative version. Okay. So the new score is also a sum, just like before. And when the sum exceeds a constant control limit, the process is out of control. The component now is going to be different. Previously, we had yi minus mu, and now I'm just saying wi. We develop what the new component should be using a hypothesis test. And the hypothesis test is mu equals mu naught versus mu equals mu 1. So this part here is unusual. Usually you would have unequals mu naught, but I'm giving a specific alternative, mu naught, mu 1. Then you can do a likelihood ratio test, and it turns out that based on the likelihood ratio test, the wi should have this form. I'm not going into details with the likelihood ratio test. This first part is as expected. This is exactly what we had before. But now, in addition, we are subtracting something. And what we are subtracting is exactly the halfway point between the null hypothesis, mu naught, and the alternative. So, yeah, I basically said this already. This is what we had before, and now we have the same thing minus the midpoint. To make it a bit more interpretable, we reparameterize this now as a function of sigma. What are we trying to make interpretable? We have to choose what the mu1 should be. What should the alternative be? And of course, you can make up numbers out of this clear blue sky, but it would be nice to have an idea of what it means. So we are parameterizing this the midpoint halfway between mu0 and mu1 as a multiple of sigma now, because sigma means something to us. It's a standard deviation. So for example, if we chose a multiple of 0.5, then we can compute this, and then this corresponds to mu1 equals mu0 plus sigma. So we are testing for a mean shift of 1 sigma. The alternative is 1 sigma above the null hypothesis. Yeah, and so to detect the increase in the control limit, we define the following score. We take the maximum of 0, which prevents it to be a negative score, and the previous score plus the new observed difference minus k times sigma. And k times sigma is also called the slack, because the function s plus will only start increasing if the additional contribution here overwhelms the slack. So it's a mean adjusted CUSUM that is testing for an increase. This is very similar to what we had before with the regular CUSUM. The difference was the regular CUSUM, we didn't have a max here, right? Well, we didn't have a control limit, so we weren't testing for increases or decreases, so we didn't need a maximum. And we had basically this component and this component. Yeah, this one and this one. We didn't have the slack. Okay, let's see. Here's an example with the data that we have seen before. Our mu is 6. Here are the y's. We compute the deltas as before. This is all as before. And now we compute the S plus function. So looking for an increase, mean adjusted. And we have to decide, well, what am I testing against? And I'm testing here against an increase of 1 sigma. Oh no, so this is sigma equals 1 was already 1. But we're testing an increase against 1 sigma. We have shown that 0.5 equals k, test against an increase of 1 sigma. This means the slack of k times sigma is 0.5. Okay. So going back to the function, we have what we had previously, plus delta, this is delta, right? Y minus mu 0, minus the slack. The slack is 0.5. So 6.9 plus 0.9 minus 0.5. So the increase here, 0.9 minus 0.5 is 0.4. Then the next item is minus 0.3. And then we subtract of that the slack, so minus 0.5, that's minus 0.8. 0.4 minus 0.8 is minus 0.4. And since we can't go lower than 0, then there's a 0. The same thing here, minus 0.8. And we can't go lower than 0, so we remain with a 0. Here we have plus 0.8. We subtract the slack, 0.5. We end up at 0.3. At 0, we still are at 0.3. Here we have minus 2.3. We subtract the slack, minus 2.8. Well, and even if we add that, we're still going to be at 0. Question for you, what is that last value? Here are some possible answers. You can pause the video to calculate, and I will move on to the next slide. We have just tested for an increase. Now we're testing for a decrease. And the decrease function is actually exactly the same except for this minus. So what we're doing is, rather than before we subtracted the slack, right? So rather than increasing the slack and looking at negative values, I'm turning it around. I'm making the negative contribution positive, and then I can still decrease the slack and I still have the maximum up there. Right? So I'm testing against the decrease by just flipping this sign. Well, this is also called the mean adjusted CUSUM, but testing for a decrease. Here is the same example as before. We still use a slack of 0.5. And so we subtract that, but we first have to flip the sign of the delta. So 0.9 is minus 0.9. We subtract 0.5, then we are minus 1.4, but we can't be below 0, so it's 0. Minus 0.3 flipped is plus 0.3, minus 0.5 is minus 0.2, but we can't be below 0. Same thing, can't be below 0. 0.8 flipped is minus 0.8, subtracted minus 0.5 is minus 1.3, but we can't be below 0. Here we have a bit more luck. Minus 2.3 flipped is plus 2.3, minus 0.5 is 1.8. And we're adding the 0 up there, right? But yeah, adding 0. So question for you is, what is that last value? I have 5 different choices. I leave this up for you to calculate. And this ends this segment.